So previously we had this discussion about a hollowed cathode lamp, HCl, that goes into the machine. And I kind of drew a diagram for you here in the beginning just to kind of start talking about the lamp and what it does and the things to watch out for. If you really want to see a picture of a hollow cathode lamp, this is what one example of a lamp looks like. Nowadays they're all made very similar. It will look something like this. The insides might be a little different, but as far as the shape and as far as the overall look of a lamp, they're pretty much universal. You can put this lamp into one manufacturer, and then you can take that lamp out and put it in a completely different manufacturer, and it will still work. So it's kind of like who knows, a SIM card for your cell phone. These SIM cards will typically work in most phones. You just take them out and switch them to a different one, and then you're perfectly okay. It will still do the job that it's supposed to do. So that is a hollow cathode lamp right there, front and center, right there looking at you. Okay? On the inside, we talked a little bit about the internal workings. We said that there was an electrode down here at the bottom, then one that's kind of pushed over to the side, and we said the tip of this thing is where the energy comes out, and down here in the back end, that's where it gets plugged in to the instrument, and that's what creates a voltage source. Here's another picture of a lamp. This lamp is made a little bit differently because it has this telephone cord back in the day for you 80s people and 90s people before cell phones came out and cordless phones. And then this gets plugged into the machine itself. You don't really see these anymore. These are somewhat outdated, and the instruments that required them are basically no good anymore. So this is just another example of something that you probably won't see in a laboratory, but it kind of gives you a precursor to what was there beforehand. And then up here at the top, this is your traditional lamp here that just basically gets plugged into the machine. It just requires a simple twist and a turn, and you are all set. All right? Okay, so we need to talk about how the lamp does its job and the pieces and parts that make this thing up. And the very first thing that we're going to focus on is the way the lamp is made. All right, so here's the lamp, and there's the front end of the lamp. And I said that one of these electrodes down here at the bottom, it's more or less a little bit fatter, a little bit bigger. And you will see this very evident in the lamp when you see one in person. This area is pretty special because this is what houses the metal of interest. All right, so for example, if I'm trying to measure copper, then this area would contain copper, and that's copper metal. And this area is going to get sacked with voltage. And that copper is going to eat that voltage up. It eats that energy. And the electrons will settle back down. And when the electrons settle back down, they will give off specific wavelengths or specific energy. And that is how the lamp does its job the proper way. Okay, so that's one of the reasons that the voltage is pretty important on the lamp. You are controlling how much chocolate you're giving the kids. You don't want to overload them. And then the copper that's in the house, here in the bulb, is going to eat that chocolate up, and it's going to get excited, and then those kids calm back down, and when they do, they give off that energy in form of a light beam that we can take advantage of. All right. There's another little piece that sits over here to the side, and this is going to be a long metal rod. It'll be very thin, very narrow, but it will be there. You might have to look for it a little bit, but you'll see it. The purpose of this stick or rod or probe, whatever you want to call it, it's called the sputtering rod. So what happens is that sometimes copper will take this energy up and the electrons spit out that energy back, But in the meantime, it generates maybe a charged copper that goes out into the atmosphere of the bulb itself. And if we're lucky, that copper will slam back into the electron again, and it will redeposit itself back on the metal casing of where it came from. All right? But we know that sometimes this is not going to happen, and there's nothing you can do about it. It's out of your control. So if the copper is not going to go back and be deposited back where it came, we just don't want this copper to float around in the bulb and pretend like everything's okay. Because over course of time, what might happen is that you will have a buildup of copper in the bulb and it will start to block the light path and no more light will go through because of that. So we don't want that to be an issue. So what we do is that we include a rod, and that rod is going to be negatively charged. And because the rod is negatively charged, any of this that happens that doesn't go back to the casing, any of that happens will be deposited and attracted to the sputtering rod. And that's that process. We call it sputtering. The lamp sputters, it spits, and it spits these metals out. And these metals fly around in the bulb, but we don't want them to be deposited anywhere they want to be deposited. So as a backup, we have this negative rod on the inside, and that negative rod will attract these metal ions and will trap them in this area. And in doing so, we can make sure that copper never gets deposited on the lamp itself anywhere it wants to be, and it keeps it very clean. The problem is that over time, you're going to see a smudge area around this sputtering rod. And the smudge area will be silver, metallic-y, gray-looking color. And the reason is because those are the metals that are actually getting deposited in that area. So some people, when they look at these bulbs and they see this gray area, the gray area makes them think, oh my gosh, this is a blown bulb. It's not very good. And actually, it's anything more so. Because this bulb has to sputter. And by looking at that metallic area, I know that the bulb is actually working because of it. If I do not see a gray area like that that's getting deposited onto the lamp, then I'm going to have to question, is the lamp sputtering at all? Because if it is sputtering, we should see a gray, silver, metallic area on the lamp. None of the lamps are completely clean. None of them are completely see-through. You will always see this area that's associated with the bulb, and it will always be around the sputtering rod every single time. And that's the purpose of the sputtering rod itself. All right? Okay, so if I go back to this main picture, this looks a little bit different. Okay? So here is this main piece that's here in the center of the lamp, and that main piece is probably going to house the metal of interest that I want to measure. The other rod, the negative piece, you can actually kind of see here to the side. And that negative piece is going to house the metallic kind of looking cloudy area in the lamp itself when that begins to turn on and get used over the course of time. Here you can kind of see this one. You'll see a main rod that's here hidden by the label. And then down here at the bottom, you see another little stick or another little rod, and that rod is going to be negative, and that's going to attract all the positives to that lamp. Okay? In the diagram itself, we have certain names that we give these. This piece here that houses the metal, that is going to be called the cathode. All right, so let me write that because that doesn't show up in the picture too well. So this area is going to be called the cathode, and the cathode is going to house the metal of interest that we are using in the AA instrument. Here at the bottom, this red line, that is the sputtering rod. And that will allow me to make sure that the metals don't get deposited wherever they want to get deposited to. And that is called the anode. So this sputtering rod is the anode of a typical galvanic cell or battery or whatever you want to call it. In this case, just a simple little light bulb. If you look at this diagram, you'll also see the voltage source. I don't really have to talk too much about that because that's just basically where it plugs into the machine. In equivalent, if that was a light bulb that you were screwing in at home, that would be that metal piece that goes into the socket. Okay? This is typically a glass enclosure. We never really see plastic at all. We've already kind of mentioned that these are glass bulbs and you have to be careful not to break them. But what we haven't mentioned is what they're filled with. Okay, and here it says buffer gas. And buffer gas is great. That's a good term to use. However, it doesn't really tell me anything at all about what a buffer gas is or what it does or how it does its job. The gas is typically filled with buffer. That buffer is either neon or argon. Now, there are some alternative bulbs that are out there that might not use one of these two, but I almost guarantee you every single time you take a look at a bulb, it's filled with neon or it's filled with argon every single time. Okay? What happens is that when you apply voltage, the voltage actually goes into the buffer gas as well, and it causes the argon or neon to ionize. And because they are ionized, these things are noble gases and they don't really like that at all. And they're ionized to a positive charge. And then they slam into the metal and they knock it off of its cage and they rip the electrons that they need from that throughout that process. And this creates an atomic cloud, is what we call that. And that's really the process of sputtering, right? A while ago, I said the voltage goes into the metal, it causes the metal to sputter out and kick out electrons, and then that calming down effect is what gives off the energy. But there's actually more to the story than that, and that's due to the buffer gas. And it's actually the buffer gas that's getting charged and then that is slamming into the metal and allowing the metal to be discharged off and then allow it to do its thing that it needs to do. So there's a middleman, and that middleman is neon or argon. But it's still called sputtering, and we still have a sputtering rod to take care of that issue with a metal getting deposited. Okay? All right. So the problem with Walsh back in the day when he was trying to sell his instrument is that this lamp was very specific. And it was a very hard sell because what you would have to tell someone is that the lamp will look for one element. And that means if you want to look for 20 different elements in your laboratory, 20 different metals, you would have to have 20 different lamps. And who on earth would want to buy that kind of an accessory to a tool or an instrument to use in a laboratory on a daily basis? So this was very expensive, and the maintenance on it was also very expensive because of that reason. So this is one of the reasons that AA took a while really to catch on into the field and in the laboratory because of the lamps that were associated with the machine. Now we kind of often say 70 plus elements that you can detect with an AA instrument. Well, that also means that you might have to have 70 plus lamps for the AA of the instrument. And if these are $1,000 a piece, then you're looking at $70,000 in light bulbs only if you want to detect every single metal on the periodic table. Okay? So, that's the story of atomic absorption and the lamp role. That lamp is very important. And that lamp has settings that have to be made by the user. And if you do not make those proper settings, nothing will happen. One more thing before I finish this video up is that this lamp has to be aligned. It's got to be aligned with the detector. So I'll plug the bulb in to the machine, and that's supposed to give me light energy that goes through a flame into the machine. And then that hits a detector that sits over here looking for the light bulb. The problem is that this area for the lamp wiggles. When I take the bulb out and when I put a new bulb in, or when someone else uses it before I do, the area that the lamp gets plugged into moves back and forth, up and down, left and right. And over time, that will slightly move the lamp as well. And if the lamp is slightly moved, what happens is that I have a possibility of missing the detector out of the other end. So I have to do what's called optimize the lamp. And what that means is basically on the lamp port itself, there's typically two settings, sometimes in screws, sometimes in a dial, that I will have to turn. Okay? And one of these screws will make the lamp move left or right. And one of these screws will make the lamp move up or down. And what I do is that in the optimization, the machine will turn the detector on and it will give me a signal. And let's say that that signal is maybe halfway up. Well, what I do is I start with one screw and I turn it and I slightly turn it in one direction. And then I watch what happens over here to this meter. Does it go up or does it go down? What I want to do is maximize the signal. So I'll turn it in one direction and I see if this green bar can go up or up or up or up or up. If at a certain point I'm turning it and the green bar goes down, I stop because it's becoming out of line with the detector. And then I choose the other screw and I turn it in one direction, it doesn't matter which one. And then I slowly turn and I see if I can get this green bar to go up and up and up again. If I can, and then this is where it kind of tops out, and as I continue to turn, it starts to fall again. That area is the maxima that I want to see. And that lamp is now optimized because of that. So that's one setting that you have to do every single time you run samples. You have to make sure that the lamp is set properly, and it has to be optimized with the detector. One screw turns it left and right, one screw turns it up and down, and you fiddle with the lamp position until you get the detector centered with the light beam, or really the lamp centered with the detector. All right. On the machine, if you're using our newer one, this is going to be close to a 1 absorbance. At that 1 absorbance mark, that's a pretty good number to go with. There'll be a black area up here at the top that the green bar hasn't made it to yet, and that's okay. You don't want this to peg out. You don't want too much light to go into the detector and oversaturate it. If you're dialing the screws, and let's say that your green meter goes way, way above the bar, what do you do? Well, there's a button that's called Rescale down below, and that rescaling is going to bring the light source back on par with the detector so that it doesn't saturate it. It does a weird little thing with the voltage in the machine and the alignment of the machine as well. So when you hit rescale, it should bring that green bar back down so that it doesn't topple over the meter and oversaturate your detector. So you have to optimize the lamp every single time. With the old ones, with the new ones, it doesn't really matter. It's got to be optimized. Okay, so in the next video, we'll move on and we'll talk about the flame, which is another pretty important piece when it concerns the AA instrument.